Hello, I want to talk about something that Strang mentions in his book Linear Algebra and Learning from Data about CR. CR means columns times rows. And what he's talking about is this statement. Any matrix A can be expressed as A equals CR, where, let's see what does C and R stand for. R has the form of some identity matrix with a star here. And here there are k of these. The I is a k by k identity matrix. And we also have, C has k linearly independent columns. These are in fact the first k columns of A. Right, now I said any matrix can be expressed this way. There is a caveat there that I'll talk about later. But basically, you're writing A as a matrix, matrix of columns times a matrix of rows, and these rows have a very nice form. Identity matrix and then some stuff. Right? Now, certainly this R looks like the RREF of A. But when you do RREF, you don't usually think of RREF in this way. You don't think of recovering the original matrix by multiplying the RREF by a matrix of columns. That's not what you do. Usually when you do RREF, you just reduce A and you come up with R. But in fact, you can recover the original matrix A in this way as a matrix of columns times the RREF. And in this video, we'll talk about why. Let's keep going. Why is R the RREF of A? Now note for one thing, R and C are not necessarily the same size as A. Here, if we have, in this case we have k columns, these are k linearly independent columns, and that means that R has k linearly independent rows. You can see the rows of R are linearly independent. That's what the I matrix does. There's no way to make any combination of these rows and get 0. Because the identity matrix has ones in separate columns. There's no way to zero out all of the columns. Now, since this is a k here and I is a square matrix, there are k rows also. Now, this k may not be the same size as the size of A. But in fact, it's the same as the rank of A. Rank is the number of linearly independent columns of A. As long as C has the same number of rows of A, and R has the same number of columns of A, then this dimension will work out. You'll have the same number of rows in A as the same number of rows in C. The same number of columns of A as the same number of columns in R. That's how matrix multiplication works out. Okay, I'm going to pause here and move down. Go down. Now, I could pad the R and the C with zeros, and that wouldn't change anything. And we'll see that down below as well. Okay, let's look at a simple example of RREF. Okay, suppose we have a 4 by 4 matrix, and it reduces to this RREF. Right? That's possible. That would be the case if A has rank 2, that is 2 linearly independent rows or 2 linearly independent columns. Now, what does this mean in terms of the homogeneous solution? We've seen before that you can get homogeneous equations out of this. 2 homogeneous equations. And those 2 equations are, from the first row here, we get, if my 4 variables are x1, x2, x3, x4, I get x1 and then 0 plus d11 x3 plus d12 x4 equals 0. Second equation is similar. Now this x1, x2, x3, x4 can be thought of as coefficients in a matrix vector equation. This doesn't appear to say anything about the columns of A, but actually it does say something about the columns of A. Let's write A as C1, C2, C3, C4, where in this case we suppose that these 2 columns, C1 and C2, are linearly independent. All right, so let's see what happens here. we can write the homogeneous equation. What's the homogeneous equation? AX equals 0. AX equals 0 is the homogeneous equation. Now, what Strang emphasizes is that matrix vector multiplication can be thought of as a column, as linear combination of columns. So the homogeneous equation can be written, if I do the matrix multiplication A times X equals 0, where X is the column vector, X1, X2, X3, X4. If I think of that as a linear combination of columns, what I would get is X1 times C1 plus X2 times C2 plus X3 times C3 plus X4 times C4 equals 0. Now note these C's are columns. I probably should have put arrows over them to indicate they're columns. Just keep in mind that these C's are columns. There, I went back and put arrows over them so that you would remember that these are columns. Right. So these C's are columns. So this is the homogeneous equation corresponding to the RREF that we showed above. Right? All right, so let's see what this implies about the columns. Let's plug in for X1 and X2. We have equations for X1 and X2 up here, right? This means that X1 is equal to minus D11 X3 minus D12 X4. X2 equals minus D21 X3 minus D22 X4. So I can plug that in for X1 and X2. And we're going to get some relationship between the columns. All right, so what do we get when we do that? All right, so I plugged in those, as I said, X1 equals minus D11 X3 minus D12 X4. X2 equals minus D21 X3 minus D22 X4. And then I have my X3 C3 plus X4 C4 equals 0. I've just plugged in those relationships between the coefficients into this linear combination equation. So let's work this out. Let's group all the terms with X3 and all the terms with X4, and we get this. Now, this relation has to be true for all X3 and for all X4. Doesn't matter about X3, doesn't matter about X4. So what does that mean? That means that these coefficients have to be 0. And this gives us the relationship between the columns that we want. See here? We get C3 is this linear combination of C1 and C2. The C4 is this linear combination between C1 and C2. So we can see that there's kind of a dual relationship between the coefficients and the columns. Here we had a relationship between the coefficients x1, x2, x3, x4, and we used that and plugged in and got a relationship between the columns. Okay? So in this chapter, we're talking about the relationship between the columns. Usually when you talk about RREF, you only think about the relationship between the coefficients. But as I said, there's this dual relationship. This is kind of related to the dual relationship in linear programming, if you know something about linear programming. All right? Okay. So in fact, if you work this out, this column relationship is exactly expressed in this matrix multiplication. If I'm going to take the third column of this matrix product, that's going to be the third column of the matrix on the right times the matrix on the left. What happens when I multiply this two-column matrix C1, C2 times this two-entry vector D11, D1, D21? Well, as you go down, D11 will pick up C1, D21 will pick up C2. And what I'll end up is a column which is in fact D11 times C1 plus D21 times C2, which is exactly this relationship. Okay, it's for the fourth column, I would take this fourth column times C1, C2, and I get exactly this relationship. So we see that, in fact, the RREF that we came up with does give us, through this column row multiplication, does recover my original matrix A. Okay, now I did mention the case where the first two columns are not linearly independent. Now you know that sometimes when you have RREF, you will have a gap. You won't have identity matrix, but you'll have some rows in here that are not identity matrix. If you work that through, it's the same thing. That means, for instance, if I had a gap column here, this second column would be a linear combination of the pivot columns. Okay, so instead of the last two columns being a linear combination of the first two, I might have the second and fourth column be linear combination of the first and third. But the same principle goes through. You could write down the same system of equations, and you could still get A as columns times rows. So this is just one example of looking at matrix multiplication in a different way. And we'll see several different ways as we go through the book. All right, that's it.